All right, excuse me. Hello and welcome to class. It's Wednesday. Um, I am a little unsure how today's live stream is gonna go. Mostly because I had an ophthalmology appointment, and so I had my pupils dilated, so I'm kind of like working in the dark. I've got all my screens dimmed as low as they can go. I'm trying to do this without sunglasses because because I think it'd look ridiculous having to wear sunglasses on a live stream. But who knows? So I'm gonna kind of test run. I might have to pop them on mid lecture. Don't be distracted. I went to the ophthalmologist, and now I shun sunlight just like any vampire would. So I might have to swap to sunglasses. I might have to do that tonight. We'll see. It'll be a longer stream, but I'm gonna try going normal. We'll see where this gets us. All right. So okay. So let's go ahead and dive. Thank you, Stephanie. I appreciate your vote of confidence. Okay, so today we are going to begin chapter 7, which is an introduction to quantum chemistry. Whoops. Oh, hang on. There we go. All right, so this is going to be an introduction to quantum chemistry. And one thing that I want to say up front is because we have an exam, it opens a week from this Friday. So not this Friday, but a week from. So about 2 weeks in the future, exam 3 is opening up. And exam 3 will definitely contain chapter 5 through 6, and I'm going to put some or all of chapter 7. All right, so this material will be on exam 3. I might pick a cutoff, so it may not contain entirely all of it. Part of it depends upon how quickly we move through it. So we'll know. I'll have a better idea about how much of chapter 7 will make it onto the third exam. Probably by next Monday. So, anyways, all that to say is exam on the horizon. Some of this will definitely make it there, especially the early stuff. Some later stuff might get cut out, but we'll take that as it comes. All right, now chapter 7 is about is an intro to quantum chemistry, and there's one thing that I do want to say before we get going. So it's about quantum chemistry, and and it really is an introduction. All right, it is an introduction. There are a lot of simplifications made in this chapter, and there are going to be moments. Most likely, some of you may have questions that that I'm unable to answer at this moment in time, and the reason for that is so quantum mechanics is as a chemistry major, everybody's got to take it. It's an upper division class, and the prerequisites for quantum chemistry, the class, it's its own class, and the prerequisites not only include a year of general chemistry, but also you've got to have like 4 semesters of calculus and a year of physics, none of which are prerequisites to this course. So we are going to be I am going to be simplifying things a lot. The book is, and there may be times you may pose questions where my answer is, take 3 semesters of calculus and then get back to me. So the answer is some question. I'll be sorry. This intro is almost as confusing as quantum mechanics itself. I won't be able to explain everything here because we're not all equipped with the math. So, anyways, I just wanted to preface that there's a lot more to this. It's a very complex topic, and it's also awesome. It's kind of the merger of chemistry and calculus. So it was a ton of fun to take. Very challenging class, but anyways, this is going to be an intro, and you don't need to know any calculus or physics to be able to follow along in this class. I'll teach you what you need as we go. All right, and the first thing that before we can get into the quantum concepts or topics, we need to do an introduction where we need to talk about light. All right, we need to talk about light. Now, light is it's one of the, light is pure energy. Okay, pure energy. There are 2 fundamental quantities in our universe. There's there's energy and matter, right? Matter has mass, energy does not, and light is pure energy. And I'm sure you all are familiar with the idea, have been exposed to the idea of the particle wave duality of light, that light has wave-like characteristics and particle-like characteristics. One of the things that we learn from quantum mechanics is light is not the only thing that has particle wave duality. Turns out everything does. Everything does, and the degree to which something behaves like a wave versus like a particle is determined by the mass. The larger the mass of an object, the more particle-like its behavior is, and the lower the mass is, the more wave-like its behavior is. And light is energy, and energy has no mass. So, because light has no mass, it is the closest thing we get to being a pure wave as anything that you'll encounter in the universe. So, we are going to be operating under the assumption that light is a wave. You all know it has some particle duality to it, but it's best described as a wave in most instances, and that's what we're going to be moving forward with. Now, there are a few characteristics of waves that we need to be familiar with. So a wave can be described, is best described as a sinusoidal function, right? So oh man, that is bad. I apologize for the wobble. This is the one area where the Microsoft Surface doesn't, there we go. It's a little better, a little smoother of a curve. Okay, so a wave is best described by a sinusoidal function, and there are a few kind of features of a wave that you need to be familiar with. The max value, these are called crests up here. So this is the crest of a wave, is the highest point in the sinusoidal function. The lowest point, these are called troughs. All right, so you've got the crest of a wave, you've got the trough of a wave. If you measure the length from crest to crest, this distance, which we label lambda, is called the wavelength. You could also measure the wavelength from trough to trough. This is also lambda, and lambda is what's called the wave length. All right, so wavelength, which lambda is the lowercase Greek letter for L, and it is an actual length. It's measured in meters. Nanometers is pretty common. Any length unit can be is appropriate here for the wavelength. You also have, so that's the wavelength there, something called the amplitude. If you measure the distance between the baseline of the sinusoidal function to either a crest or a trough, this is the amplitude. All right, and the amplitude is represented by a capital letter A. All right. Now there is we're not going to do much with amplitude this semester, but I want to point it out so that you're aware of it, you're familiar with it. So you've seen the wavelength. Wavelength, we're going to do a lot with waves, talking about the wavelength, but we're also going to use something called the frequency quite a bit. And with wavelength, you can point out, looking at one wave, it's easy to illustrate like, oh, there's the wavelength. Frequency, it's harder to do, to introduce that topic by looking at one wave. So I'm going to compare two waves side by side. All right. So so consider these two wave functions. So there's the first. These are roughly the same length. All right. I'm going to call this wave 1. I'm going to call this wave 2. If you look at, I'm going to actually need a little longer for wave 1 just to illustrate this. All right. If you look at, and you'll see why, if you look at the wavelength for wave 1, we got to measure crest to crest, right? The wavelength would be about this long. So we'll call that wavelength 1. And now let's compare this to the wavelength of wave 2. Again, we're going to go crest to crest. This would be the wavelength for wave 2. Now you can see that the first wave, wave 1, has a longer wavelength, a larger wavelength than our second wave, right? The second one's tiny, the first one has a large wavelength, all right? Now frequency as a quantity is defined like this. All right, so this is the definition of frequency. Frequency is the number of crests, or you could do this with troughs, but I'm just going to roll with crests, that pass through a fixed point over a given time. All right, the number of crests that pass through a fixed point at a given time. I'm going to lengthen my thing here so that these two are. All right. Now frequency is the symbol for frequency is the Greek letter nu. So this is an NU is how you pronounce that. It's the Greek letter for N. It kind of looks like a V with a weird little squiggle on the end of it. All right, that is the frequency. And here's the way to think of it. Let's assume, so looking at comparing wave 1 and wave 2, let's assume that we're looking at a snapshot of each wave. All right, we're looking at, okay, how in this, let's say that we're looking at 1 second of time. All right, so this span here, from here to here, is 1 second. All right, in 1 second, the number of crests that pass through, if you had a fixed point that's like being held like right there, and then you've got your waves moving through, right? That's what we're seeing going here. For wave 1, the number of crests that would pass through that point over 1 second is 1, 2. Whereas the number of crests that would pass through for wave 2 are 1, 2, 3, 4, 5, 6, 7, 8. So you can see that a lot more crests pass through a point in space over that time for wave 2 than it does for wave 1. So because of that, because more crests are passing through in a given time, you can see the wave is tighter, the oscillation of the wave is tighter. We say that wave 2 has a larger frequency than wave 1. And you'll notice that the opposite is true for wavelength. If we're talking about lambda wavelength, the wavelength of the second wave is smaller than the wavelength of the first wave. All right? So these two things are inversely proportional. Real quick, before we dive into that, I'm going to spend a little time there. But the units for frequency, because it's the number of crests, which is just a number, that passes through a fixed point over a given time, it's a unit per time. The units are 1 over time. It could be any time unit, could be given for the frequency. But instead, well, not instead, the most common unit for frequency is 1 over seconds. All right, and this unit is renamed. It has a special name. It's Hz, because the per second, 1 over seconds, is called hertz. All right. So hertz is the most common frequency unit, Hz, and it's literally 1 over seconds. And if you're wondering, you're like, wait a minute, I know hertz, not the rent-a-car, but I'm familiar with them from computers, right? Processor speeds are measured in, oh my gosh, this is gonna date me. I almost said megahertz, and that's how you know you grew up in the 90s. They're measured in gigahertz now, right? But it's which giga is and mega, both of them are unit multipliers. They're modified units for in the metric system. So they're measured in hertz. You're like, why are processor speeds clocked in hertz? Because your computer processors are measured, their speed is measured in how many operations they can get done in 1 second. All right, it's operations per second when you're talking about processor speeds. For light waves, and for waves in general, it's crests per second. It's how many crests are passing through a point in a given second. All right. So those are the units for frequency. The units are hertz, and as I said just a minute ago, you'll notice that frequency and wavelength are inversely proportional. If the frequency of wave 2 is larger than the frequency of wave 1, that means the wavelength of wave 2 is smaller than the wavelength of wave 1. When one increases, the other one decreases, and I want to explore that relationship a little bit. So we just said that the frequency of a wave is inversely proportional to the wavelength of a wave. Again, you're familiar with this song and dance, right? You know that if we want to change this proportional sign to an equal sign, we are going to need to multiply one side of this equation by a constant. All right? And we can solve for what that constant is if we multiply both sides of this equation by lambda. All right, wavelength cancels on the right side of this equation. And we get oh, hang on, I don't want that in blue. We're going to get frequency, the frequency of a wave, times its wavelength is equal to c. All right? And if you're wondering, okay, what is that constant? You're like, I'm not wondering, but I know you're going to tell me. Which is good, you're anticipating my my teaching method. Let's look at our units and figure out what this constant is. Frequency is measured in hertz, so that's per seconds, right? 1 over seconds. And wavelength is measured in distance, right? The most basic distance unit is meter. All right? What type of unit is meters per second, right? Is length per second? That's a speed, right? That's a velocity. This, length per second, is a speed or velocity or rate, right? It's like miles per hour. That just has a different length unit with English units. All right? It's a speed, it's a rate. And what is the speed that we're talking about? Well, this has a name, and this is the constant speed of light. Well, that got a little cramped. Let's pull this in a bit. That quantity, that constant c, is called the constant speed of light. Now, you may have heard that thrown around before, like, oh, the constant speed of light. But that's because light's speed literally is constant. Whenever you have a wavelength of light that is moving through the universe, it only goes at one speed. And that speed is 3.00 times 10 to the 8th meters per second. All right, that is the constant speed of light. Now get this. Think about this for a second. There's tons of different light waves out there, right? Lots of different, not just the visible spectrum, the colors we see, right? But there's X-rays, there's radio waves, there's gamma rays, all this kind of stuff. All the things that give superheroes powers in the books and the movies, right? But get this, and they all have different energy levels. They all have different wavelengths. They all have different frequencies, but they all move at the same speed. All right, that's crazy to me. It doesn't matter if it's a high energy wave that'll give you cancer if it hits you. It doesn't matter if it's a low energy wave that couldn't hurt you if it tried. They're all moving at the same rate. It's bizarre. I have no idea why, but it's true. It's cool. And it doesn't matter what specific frequency or wavelength you're dealing with. If you multiply the frequency of a light wave by its wavelength, it'll always come out to be the constant speed of light. All right? So let's do an example. We've made it far enough into chapter 7 where we can start doing some math. Oh, not quite yet, actually. Let's put that on hold for a minute. We'll come back to that. Before we do an example, Let's talk about. So I said all light's moving at the same speed, and I verbally articulated that even though that's true, different wavelengths of light will have different energies, right? Light waves with different frequencies will have different energies. Some, as we've said, like the radiation at Chernobyl can give you cancer and kill your cells. Others are benign, like they couldn't hurt you if they tried. And what determines whether or not a light wave is dangerous to us is is the energy of that wavelength. If it's high energy, it can burn you. If it's low energy, it won't. And energy is directly proportional. The energy of a photon of light or a wavelength of light. The energy of a photon of light is directly proportional to its frequency. All right? And again, this is going to give us an equality. The energy of a photon of light is equal to the specific constant that we multiply frequency by is h. H is known as Planck's constant. Planck is spelled like Planck because he was German. Planck's constant is equal to 6.626 times 10 to the negative 34th, and its units. If you look at it, let's break this down. Energy has units of joules, right? And we know frequency has units of 1 over seconds. So if these two sides of the equation are going to be equal, we need to multiply it by joules times seconds. That way seconds can cancel and we're just left with joules. So the units, for Planck's constant are joules times seconds. All right, that is the value for Planck's constant. I got super excited. What was it? Last year, 2019, when my wife and I were watching season 3 of Stranger Things. I don't know how many of you have watched it. Chances are a good number of you have. Right, it's the highest streamed show on Netflix, and they need the digits for Planck's constant to unlock a code in the door, and Dustin's calling up his super nerdy girlfriend to get it because he doesn't remember what it is. And at that point in the show when he's like, I need the values for Planck's constant, I was like, I literally said 6.626. It turns out they needed 2 more decimals, and so I didn't even have enough information, but I knew what it was. I was watching it with my wife, and I think my brother was around too. They were both super impressed. So anyways, that's my fun little Planck's constant anecdote. If you haven't watched Stranger Things, you owe it to yourself. Go do it. And when you get to season 3, this comes in clutch, right there at the end. So don't let anybody tell you that chemistry doesn't have any real life applications. All right, now that we have this equation with for relating the energy of a photon or a wavelength of light to its frequency, we can solve a whole mess of problems. And again, we're going to be using these two in conjunction. Energy is equal to Planck's constant times frequency, and the frequency of light times its wavelength is equal to the constant speed of light. Again, I know I have this just written above, but I'm rewriting it because I would highly recommend, as preparation for the exam, that you write out an equation sheet. That's not a negative, that's a positive. Write out an equation sheet of all the algebraic expressions and constants that you might use. There's a mess of equations for the gas law stuff, which will all be out in force on exam 2. And so I would definitely add these 4. Right, these 2 equations and 2 constants. You want to write these down so you have them at the ready when you sit down to take exam 3. If you're still in my class and taking exam 3 for me. If not, then, do whatever Professor Mahoney tells you. All right. Now that we've talked about the relationship of the energy of a photon of light to its the relationship of the energy of a photon of light to its frequency, we can do the following example. A photon of yellow light has a wavelength of 400 nanometers. And a photon of violet light has a wavelength of 600 nanometers. Is that right? No, that is not right. Sorry. I feel like yep. I am, I'm actually, I am slightly dyslexic. Sorry, yellow light is 400 nanometers. Violet light is 600 nanometers. I apologize. All right. That's a statement. What is this question asking? Calculate the energy of each photon to determine which is larger. Or I should say not larger in energy, I should say higher in energy. All right, so we're given a couple of wavelengths. We're asked to calculate the energies of each photon and the energy of each photon to determine which one is higher. And before we dive in, I just want to say, when you hear, because you're going to hear problems, when you hear a photon of light, the photon is a word. This is a word that describes a single light particle. All right. As I mentioned earlier, and as you already know, light has a duality to it. It sometimes behaves like a wave, sometimes behaves like a particle, and a photon is one individual particle of light. All right, so it's one individual wave of light moving out there through the universe. So when you hear, like in this problem, photon of yellow light has this wavelength, the photon of violet light has that wavelength, you're going to calculate the energy of that individual piece of light, so to speak. All right, that's what that word photon means there. Now, let's go ahead and move forward and start solving this problem. So, the photon of yellow light. So let's look at what we need to find and what we're given. So we're being asked to find energy, right? Now, energy, the energy of a photon of light has an equation. Energy is equal to Planck's constant times frequency, and we know Planck's constant. It's a constant, just like the ideal gas constant. It doesn't change. It's always the same. Now, that's what we're trying to find. What are we given? We are given the wavelength of each photon of light. The wavelength of yellow light, the wavelength of violet light. Now, the question is there a way to connect wavelength and frequency? And turns out there is. The wavelength of a photon of light times its frequency is equal to the constant speed of light, which is also a constant, we know. All right? And so this equation relates wavelength and frequency together. Now check this out. If you solve this expression for frequency, so that wavelength cancels out of the left side, you get an expression that frequency, the frequency of a photon of light is equal to the constant speed of light divided by its wavelength. You can substitute in frequency into your expression for energy, so that energy is equal to Planck's constant times C over lambda. All right, energy is equal to Planck's constant times the constant speed of light divided by its wavelength. So when you look at this expression, we know Planck's constant, we know the constant speed of light, and we know our wavelength. So now we can find our energy. The one catch here is that when you go to plug these quantities in, so for example, if we're doing yellow light first, energy is equal to Planck's constant times the constant speed of light over lambda. When you plug in your quantities, Planck's constant 6.626 times 10 to the negative 34th. This is joules times seconds. The constant speed of light is 3.00 times 10 to the 8th meters per second, over our wavelength is 400 nanometers. There's a problem, and that problem is our length units do not match up. We have meters in our numerator, nanometers in our denominator, and so we need to do a unit conversion first to convert our wavelength from nanometers to meters in order for our units to cancel. So we got to set up our unit conversion. Nanometers goes in the denominator because we want it to cancel. Meters in the numerator. 1 nanometer is 10 to the negative 9 meters. So nanometers cancel, and we get a wavelength of 4 times 10 to the negative 7th meters. All right, so this is what we need to plug in to our denominator here. Um, 400 nanometers is, whoops, 4 times 10 to the negative 7 meters. And now our length units cancel in addition to our time units of seconds. All right, now we're ready to crunch our numbers. Oops. So we got 6.626 times 10 to the negative 34th times 3 times 10 to the 8th divided by 4 times 10 to the negative 7th. All right, and you'll notice we were given a length for both of these that only have one sig fig, so we can only have one significant digit in our answer. The energy for yellow light then is 5 times 10. Let's see. Times 10 to the negative 19th joules. All right, that is the energy for yellow light. We still need to find the energy for violet light, and so that we can compare the two. So for violet, the nice thing is all the algebra that we did to find the energy of yellow light all still apply. So we're still going to use the same equation that we derived. Energy is Planck's constant times the constant speed of light over wavelength. The values for Planck's constant and the constant speed of light have not changed because they're constants. All right, and this is all over our wavelength, which we do have to convert to meters, by the way, just like we did with 400 nanometers. 600 nanometers is 6 times 10 to the negative 7th meters. All right, so now meters, our length units cancel, our time units cancel. And now we crunch our numbers. And again, just like before, we can only have one sig fig. Our energy for our photon of violet light is oh wait, did I mess this up? It's 3 times 10 to the negative 19. Oh, here, hang on one second. I think I botched this in the original problem. Let me look back at it. I totally did. I had it right the first time, and then I flipped it around. I apologize. Okay. Sorry. For the record, I had it right the first time, and then I changed my answer, which is always a bad idea in a testing environment. It's the same with lecture 2. The wavelength of yellow light is a longer wavelength. 600 nanometers is yellow light. And I'm just looking at my notes. Yep, violet light is 400 nanometers. I apologize. So therefore, these two are backwards. This should be yellow up top. This should be violet down below. Oops. All right, let's see. Jared. Oh, did I? I did have it right the first time, and then I rewrote. Oh, wait, really? Oh, thank you guys so much for being forgiving. Here's the point that I want to come to, that I'm clumsily arriving at, is when you compare the energy level of... Oh, Kate, no worries. Thank you for being patient, everyone. When you compare the energy of yellow light to violet light, yellow light had the larger wavelength, lower energy. Violet light had a smaller energy, larger wavelength. Yes, okay. Totally. All right, so there's our clumsy first example. All the math is correct. So you know, the steps were fine, the numbers were fine, but it's just they were flipped because violet light has a lower energy, higher energy, lower wavelength. Yellow light, larger wavelength, lower energy. Okay. Kate, great question. It's not so much that darker lights have that it's not the difference between dark and light, but when you look at the visible spectrum, which goes from kind of red all the way to violet. It's so the visible spectrum is structured like this. It's the irony of writing red and blue. It's red, orange, yellow, green, blue, indigo, and violet. So as far as energy goes, so this is the just to be clear and explicit, this is in the visible spectrum. So for the wavelengths that our eyes can detect, so for visible light, violet is the highest energy, wavelength of visible light, and red is the lowest energy wavelength of visible light. That because violet is highest energy, it also means that it is the highest frequency. Because red is the lowest energy, it also means it is the lowest frequency. But because it's lowest frequency and energy, it has the largest wavelength. And violet has the smallest wavelength. And everything in between matches up with that. So blue, for example, is higher energy than yellow because it's closer to violet on the visible spectrum. But so this is kind of how it ranges. Red's on one end at the lowest, violet's on the other end at the highest. And that's how their wavelengths kind of line up. So you could maybe think of it as like darker to lighter, but that might run you into trouble because sometimes, like, mentally I think of like red being a darker color than yellow or orange being darker than yellow, but yellow is actually higher energy than red or orange. So it's not so much the darkness of the light, but where they fall, where the specific color falls on the visible spectrum. Okay. All right, now, so that's kind of our introduction to light. I want to spend a minute talking about how atoms interact with light, all right? So, we all know that different compounds, different molecules, different atoms can absorb light, right? This is actually why we end up seeing color. So turns out that if you combine all the colors in the visible spectrum, that our eyes see white, right? The only reason why we see color, right? Like you look at like my red microphone, for example, that I'm looking at right now. It does have something to do with that, Kate. It definitely is related to that, and the different wavelengths. Yeah. So looking at my red microphone, the reason why I see red is because when light hits it, the material that this microphone is made out of absorbs all the colors in the visible spectrum, all the wavelengths in the visible spectrum, except red, and so red is what bounces back and hits my eye, right? That's why we see color, because materials will absorb different colors and not absorb others, and so that is kind of what gives rise to our perception of color. All right, now I want to talk about how atoms specifically interact with light. So atoms can not only absorb light, they can also emit light. All right, so both things can happen, and so let's draw a picture, because word on the street is that a picture is worth 1,000 words. All right, so we got a proton right here, and we have an electron orbiting this proton, right? Our electron's buzzing around space, orbiting around our proton. This is a familiar sight to all of us, all right? Now, I want to ask you a question. All right? So we've got our electron, it's orbiting our proton. And I want you to think about those two particles' relationship to each other, all right? You've got your electron, you've got your proton, and there's an attraction there, right? The electron wants to be as close to that nucleus as it can because the negative charge on the electron is attracted to the positive charge on the proton, right? So they want to be as close to each other as possible. If you take the electron and you pull it away from the nucleus, all right? If you were to grab a hold of the electron and move it away from the nucleus, so it's further away. Here's the question. Is that process endothermic or exothermic? Let me rephrase that. If you're pulling the electron so that it's farther away from that proton, is it going to require you to spend energy or is it going to release energy? Let me rephrase it again. Is the electron going to fight you as you pull it away from the proton? Is it going to resist that? The answer is yes, right? You can pull the electron away from the proton, but the electron wants to be close to the proton, so you are going to have to force it. You're going to have to spend energy to move the electron away from the proton, right? So electrons, it's actually going to absorb. It's going to absorb energy to pull it away from the nucleus because it's fighting you. So you are having to spend energy to move that electron away. Electrons, or I should say, let me rephrase that. For electrons to move away from the nucleus, they need to absorb energy. All right? For electrons to move away from the nucleus, they need to absorb energy. All right? Now, okay, so this process is called adsorption. And I know I'm horrible at spelling. You're like, shouldn't that be absorption? It's not. It's actually spelled with a D. Adsorption, to move away from the nucleus. Now, think for a minute about what happens when the opposite is true. If the electron moves closer to the nucleus, hang on. What type of change in energy occurs? Oh, there we go. When the electron moves closer to the nucleus, all right, are you having to force the electron to get closer to the nucleus, or does it flow there naturally? Well, it'll flow there naturally. It wants to get as close as possible. So when an electron moves towards the nucleus, all right, when an electron moves towards the nucleus, it releases energy in the form of a photon of light. All right. So when the electron moves closer to the nucleus, energy is released in the form of a photon of light, and this process is called emission. All right. When the electron moves closer to the nucleus, energy is released in the form of light, and it's called emission. All right. Now, okay, so we've got absorption, we've got emission. And so here's where things get weird, and this is really our intro kind of into the quantum mechanical model of the atom. So you know what happens energetically when electrons move around, right? They get farther from the nucleus, they absorb light, right? They absorb energy. They move back closer to the nucleus, they release energy. And the distance that they travel, right, as they're moving away or moving towards, determines the amount of that energy. And as we know, energy corresponds to wavelength. So the colors that are either absorbed or emitted are determined by the distance the electron travels. That distance determines the energy, the amount of energy released. That'll determine the wavelength and the frequency of the photon of light that is emitted. All right? Theoretically, any atom could emit any color of light. All right? That is theoretically possible, but it's not what actually happens. That's the weird thing. It's not what actually happens. Turns out that only certain specific atoms can only absorb or emit specific frequencies of light, specific wavelengths of light. And that is counterintuitive, and it begged the question, why? Chemists and physicists, at the time the field was kind of the same, chemistry and physics, were asking why are only specific wavelengths of light being emitted by specific atoms. Sorry, I'm really quickly grabbing colors off my color palette so I can do this next part. All right, so turns out that the explanation, the answer to that question, why are only certain wavelengths of light being absorbed or emitted, led to the proposal for a new kind of model of the atom. Before, we kind of understood atoms as, okay, you've got the nucleus, all the protons, the electrons are orbiting around. But the only way they could explain why, for example, hydrogen only emitted certain specific colors, wavelengths of light, when its electrons were excited, led to the proposal that that the electrons were not free to orbit the nucleus at any given distance, but that they could only orbit the nucleus at specific distances. They could only be this far or this far, and here's why. So to explain this information as to why hydrogen was only observed to emit specific wavelengths of light, it was proposed by Niels Bohr that that the electrons were not free. Oh gosh, I'm just going to apologize right now for my circles. I can't draw them perfectly. So I'm going to do the best that I can with the wobbly digital pen that I have. So Niels Bohr proposed that electrons weren't free to orbit at any distance, but that they could only exist at specific distances from the nucleus. And here's why that was proposed. So first, when hydrogen is excited, you hit hydrogen with a bunch of energy. The electrons in hydrogen absorb that energy and move out to the outer orbit. Oops. So the electron is promoted to the outermost orbit. From this orbit, there are several different emission pathways available to the electron. For example, the electron could jump all the way back down to the first orbit, and moving that distance would release a wavelength of light at a specific energy, a specific frequency, in a specific color. Or, for example, the electron could jump down to orbit number 2. And that would release, that emission would have its own color. From orbit 2, it could jump down to orbit 1, which would release a different color of light, etc. Or the electron could start in the outer orbit and jump down to 3. That would release a different color. And then from 3, it could go all the way down to 1, or 3 to 2, etc. And what gave rise to, this is called the Bohr model of the atom. What Niels Bohr was able to do was, and other scientists, not just him, we'll actually talk about Balmer and Rydberg in just a second, is they were able to calculate using math and physics that when the electron would move such a distance, what amount of energy would be released and what wavelength of light that would correspond to. And they were able to predict the emission pattern for hydrogen atoms based on the electron traveling that distance through space. So it was actually revolutionary, and it gave us the idea that the electron wasn't free to just orbit at any distance around the atom. It could be in orbit 1, or maybe I should go like this, orbit 1, or wider, orbit 2, or wider, orbit 3, but that it couldn't be in between 2 and 3, or in between 2 and 1, etc. And the reason why this was proposed and adopted is because it was the only way to explain the data that we saw, that hydrogen only emitted light at certain wavelengths, certain frequencies, certain colors, and not others. It was explained through the quantization of orbit energy. Now that word quantum, I said this is quantum chemistry, and now you can actually see what it means, what that word means. It's kind of thrown around. Quantum is a word that it's like, oh, that's it either means hard or difficult to understand, or mysterious. Like Ant-Man goes into the quantum realm, which is visualized for us like an LSD trip. And it actually means neither of those things. The word quantized, quantum mechanics, simply means that it's broken up into kind of integer values, integer chunks. Like you can be at orbit number 1 or 2 or 3, but you can't be in between, all right? When you hear the word quantum, think 8-bit, think pixelized, think Minecraft, all right? Minecraft, you're either on one step, one block, or the next block, but there's no in between, there's no gradation, right? So that's what the word quantum means. And we say here that when you look at these orbit energies, they are quantized. All right? You can be at energy level 1, 2, 3, or 4, but there's no decimals, there's no fractions, there's no in between. It's on or off. It's binary in that sense. All right? Okay, now. I guess one last thing I want to point out. And this goes without saying, but I just want to explicitly state it. Larger values for n mean that they are higher energy because they're further from the nucleus. So n equals 4 is farther from the nucleus than n equals 2, so it's higher in energy. All right. Now, hang on. Okay. Oh, wait. Here we go. Okay, so let's talk So the orbit energies for atoms are quantized, and I said that chemists, physicists were able to predict the emission spectrum for hydrogen, right? When you expose it to a ton of energy, the specific types of light that it would emit. It would only do certain of them, and that we were able to predict them. And that came about through the work of two physicists named Balmer and Rydberg. All right, Balmer-Rydberg. Now, the Balmer-Rydberg equation, so they had a specific equation that they developed, and their form of the equation isn't commonly used, but we're going to start with it. The Balmer-Rydberg equation states that 1 divided by the wavelength of the frequency of light, sorry, not the wavelength of the frequency, that literally makes no sense. 1 divided by the wavelength of a photon of light is equal to R, which is called the Rydberg constant, times 1 over the initial orbit squared minus 1 over the final orbit squared. All right. So just to be explicit, N1 is the initial orbit, N2 is the final orbit, all right, and the electron is transitioning from N1 to N2. It doesn't have to be the first and second. It could be a transition from third to fourth, or it could be a transition from the fourth orbit to the first orbit, but that's just the N1 stands for the orbit you're starting in, and 2 stands for the orbit that you are jumping to. All right. So this was the original formulation of the Rydberg equation, but it's not very useful. 1 over wavelength is not a very useful quantity, but if you take our equation for the constant speed of light, frequency times wavelength equals the constant speed of light, and you do some algebraic magic, if you multiply both sides of this equation by 1 over wavelength times the speed of light, watch what happens. So first, wavelength cancels here and here. The constant speed of light cancels here and here. So we get an expression that says frequency over the constant speed of light is equal to 1 over lambda, your wavelength. And now you can take this and substitute in it here. Substitute it in here. So now you get frequency over the constant speed of light is equal to the Rydberg constant times 1 over the initial orbit squared minus 1 over the final orbit squared. All right. Now, nobody likes a denominator. So let's go ahead and multiply both sides of this equation by the constant speed of light. That'll give us an expression that says frequency, the frequency of the light being emitted or absorbed is equal to R times C. R is just a constant, C is a constant, times 1 over the initial orbit squared minus 1 over the final orbit squared. All right, now let's take both sides of this equation and multiply by Planck's constant. And you may be going, why the heck would you do that? I'll show you. So when you do, you get Planck's constant times frequency is equal to R times C times Planck's constant times 1 over the initial orbit squared minus 1 over the final orbit squared. And the reason why we do that is because we have an equation that says the energy of a photon of light is equal to Planck's constant times the frequency of that photon of light. So this literally now is energy, and this over here, R times C times H. R is a constant number, C is a constant number, H is a constant number. When you multiply three constant numbers together, you get a new constant number, which they just relabel RH. So after you do a little algebraic massage, you can rearrange the original Rydberg equation to a much more useful form, where energy, the energy of the emission, whether it's absorbed or released, is equal to RH, this constant, times 1 over the initial orbit squared minus 1 over the final orbit squared. And the Rydberg constant RH has a value of 2.18 times 10 to the negative 18 joules. All right, so that is the value for RH. All right, and that is this is a more useful form of this equation. All right, that is where we're going to end things for today. We'll pick up on Monday we'll do some more examples. Use kind of the Balmer-Rydberg equation or this form of it, and then we will keep working through chapter 7. But we're going to go ahead and pause there today. Thanks everybody for hanging out, showing up. I'll see some of you in office hours tonight and the rest of you on Monday. Later, dudes.